let's dive into our simple stock price prediction example. I consider this simple because it's pretty straightforward and doesn't involve that much. So here I use now the other data file, right? tpq.io would make more sense, right? So here we have seen already what is in there. Our 14 symbols with stock price data 2014, mid 2014 to yesterday. Right? Apple, Microsoft, and so forth. So I call this raw because usually I pick then one symbol and call this data. So, but this is a matter of taste and preference. If you want to follow along, feel free. Otherwise, I will push, obviously, or for sure, the result to the repository afterwards. So I'm now specifying the symbol. We can, I don't know with what we go. Maybe let's go with Google, for example, right? So now picking out PD data frames. I want to end up with a data frame, not with a series, because the series is limited. Not symbol, that's the reason why I've defined it. That we now have our Google time series here with a obviously larger drawdown starting at the end of 2021 here, but in the age of generative AI, you see these stocks have all risen quite a bit. So how do we go about this? We use supervised learning. For supervised learning, we know we need features plus labels. So all the examples, how many ever? 500, 5,000. And I want to create the sample data, the feature label combinations from the price data. So to this end, let me here generating the data, or let me call it the features first, right? And to this end, I get started now with, let's say, what we've got, the prices. It's questionable, the prices, but let's get started with what we've got. So I define here the number of lags, for example, to be 5. All right, 5 lags. And why lags here? I want to use historical data in order to predict future data. So when I open here trade application, Wonder, something that we use since many, many years. Let me log in. Here is one of my demo accounts. And I must be careful, given that I have yesterday have been teaching for the CQF. I was just inclined to say, as I said before, but it was yesterday in a different context. With my students in the CPF program is a bit more easy because I can say as the previous session, right? And I know that exactly. So here we see charts. Some of them are moving, some not. Maybe let's pick here the euro yes dollar code that's on a 1 minute bar level to see something moving. Let's go to the 5 second bar level. These are typical open, high, low, close charts. Maybe let's change. I prefer usually the Heikin Ashi. You will see changes in color. They are much better to visualize trends. And what do traders do? We are here in a trading lab, right? So I think it fits quite well into this environment. What do? They have a look at the history and try to predict the future, right? Nothing else. They are looking for patterns. They use things like, here my moving averages that are visualized here, like 3 and 10. Right, here's the faster moving one, the shorter one, and one reasoning, standard strategy also analyzed, maybe not on a 5-second bar level, this wouldn't make sense, but on longer bars, as if the faster moving average, they call it MA, simple moving average, SMA, is above the slower one, then this would be a buy signal, right? Otherwise, it would be a sell signal. Here, on the 5-second bar, even there we find some stretches where this seems to make sense, right? But this probably is not even enough to earn the, even if you would get this exactly correct and the exit point exactly correct, this would probably not be enough to cover the transaction cost. But that's a different story. The only point that I want to make is people are looking at the history and are now trying to predict whether this goes further up now or whether it will go down or will primarily use sideways. The same approach will now be implemented, but without any necessary visualization. We can visualize things, of course, but what we do in machine learning, supervised learning in our case, is that we provide numbers, right? This is just for us human beings because we can digest that much better than, let's say, numbers listed in a spreadsheet or wherever, right? Data frame, you name it. So maybe I keep this open for a second. And therefore the lags are now our history, but in numbers again and not in terms of any formation. So how do I create now my lags? I define usually something that I call calls for the columns that make up my features. That's in the beginning an empty list object. Then for lag in range 1, I start with 1, lags plus 1. Given how range behaves, I define as an F string the lag name, here lag, so it will be lag 1, 2, 3, 4, 5, meaning I lag the count price by 1 day, 2 day, 3 days, 5 days. If you work with 1 minute bars, it will be 1 minute, 2 minutes, 5 minutes. Right? So data now I add with the just define column name, I add data symbol, but shifted by lag, by 1, 2, 3, 4, 5. Therefore, if I would use range as it's often used, like simply range lags, then we would get 0, 2, lags minus 1, 4. Therefore, we wouldn't really do the shifting correctly. Therefore, I start at 1 here. Last but not least, I append the column name here. So there's an invalid syntax. It's missing the assignment operator. So how does data look like now? We have the Google price, lag number 1, 2, 3, 4, 5, and you see now the price from the 1st of July is here to be found in the second row under lag 1. So it moves 1 down, 2 down, 3 down, 4 down. And down here towards the end, also from the next row onwards, we find full data set. We have here lag 1, 2, 3, 4, 5. This gives us the 5 most previous price observations. Like in the trading app, this would mean here, now I slow it down a bit, maybe to 1 minute. We are here with that bar. This is probably not complete, this 1 minute, but here would go 1. You see this is changing. 1, 2, 3, 4, 5 of these candles I would use in order to predict something. I can go with 15, 50, whatever. Of course, when we see here the visualization, we would maybe visually take everything into account, but I can, of course, here zoom in and zoom out. And this is more or less also arbitrary. This is when I was saying, well, I just work with 5, 15, or 150, or 300, whatever. With regard to the minutes, that's not that much, right? When I go 300 minutes, that's like a few hours. That's not like 300 days. It's already more than a trading year in general. Therefore, this is just arbitrary at this stage. I go with the 5, right? So that's the data that we have. Maybe we do.
Roll up real quick to see what the transformation you did on roll to get it into the data.
I just pick the column and then create a data frame. Why a data frame? Yeah, I can add columns to the data frame, to the series object. I cannot add anything. That's simply as it is. Yeah. So there is, in other words, a difference between a series object and a data frame with a single column. Two different beasts. So we have quite a few, not the number values here. We recall JetGPT was looking for missing values here. We have quite a few. We can, in this context here, simply do a drop NA in place true. Right? Then we are getting rid of, my goodness, even with my classes, I'm having trouble here. I'd rather look over here and put there. That's bigger. So now we are having a complete data set. We can now implement something called estimation, right? We can look back, see the prices, and this is what day traders in general do, right? This is all about prices, not about returns, whatever, right? These are prices. Here I'm not dealing with any type of bar in that sense. Candle, what we are dealing with is rather something like a line, right? So we are just focusing on the one price, which is the closing price for the interval, which is here the thin line, right? But I think we are all used to these candles here. Numerically, and it wouldn't speak anything against adding the other values as well, right? Open, high, low, close. We just have close here. We could also add open, high, low if you would see a benefit in there. But let's get started with some estimation. Usually I don't do it that way, but just to keep up and keep alive the analogy to the day trading, right? We can now say, well, we use the lags as the features, and the price is basically what we want to predict. And to this end, we are dealing now with something like ordinarily scarce regression or an estimation problem, right? We want to come up with floating point numbers, and this is about estimation. So maybe let's give here a bit of structure. Stock price prediction. That's the data here. Make here generating features. And here predicting stock prices. All right, and to this end, we might do the following. Maybe I immediately dive into the neural network, right? From sklearn, this should be installed. Neural network, import MLP regressor for estimation, like ordinarily scarce regression. We can also do OLS regression, and maybe we can compare the results. Now recall what I was saying, we have 3 steps in general: model instantiation, model fitting, and the prediction step. Here it is the same. So model is now MLP regressor. I don't do any parameterization, customization here. Model fit, just doing stuff out of the box. Maybe it then raises some error for not converging or whatever. This would not be an error, this is usually a warning. Might be some other warnings in here. Model fit now. What are the features? Data. That's the reason why I've defined my list object with the column names, calls, and data symbol is the label. So I want to use the 5 historical lags in order to predict the current price or the future price, depending on what we see as the reference point. So it takes a little bit. I put in here a time so that we get a feeling for how long this takes. Now, again, what I was saying before, maximum iterations 200 reached and hasn't converged yet. For the time being, we can ignore that safely. Now, the third step would be the prediction step. Model, predict, data, now only the features. My goodness. I should sit straight in front of my machine, otherwise typing is don't mistype. So calls. What do we get? Yeah, indeed, we get values, floating point numbers. This is what the regressor is all about. It's not about classification like 1, 2, 3 or ABC or whatever. We have seen also the clustering algorithm. There, the prediction step gave us numbers of the clusters, 0, 1, 2, 3, 4, depending on how many clusters we have been looking for. So usually I would put this here into a column. Let me call it prediction. So that I can do something with it, like data prediction. Just having a look at it, plot. It somehow looks like what we have been doing before, right? So let me maybe plot the two of them, and by two I mean the symbol and the prediction itself. And you see basically not that much, right? Because the green and the blue lines seem to be somehow overlying each other. Therefore, what I usually do, I zoom in. Zooming in means we can go, for example, with the final, to get started with 100 data points. I log dot 100 data points. With this look now, we see that it's not exactly the same, right? It's rather, when we have a close look, is that the prediction more or less gives us the previous value as the next period value, right? So, but this was out of the box. Let me do some changes here. So the first change, in order to not only suppress the warning in a technical sense, but also to hopefully get a better convergence, I can increase the number of iterations here for the learning to 1000, by default it is set to 200, right? This will increase the number of iterations, and it might in the end take a little bit longer, right? But the result might be better. We cannot really judge here, but we can, for example, do a calculation, and I take these two, right? Data symbol minus data prediction, so out of the box here, squared differences over the length of data, mean squared error. There are predefined functions for that, but it's like easy enough here to do that. We get it here per element. What we should do obviously is to do the summing up. So these are the pair column, and this is 237. So let me change a bit more here. So by default, the hidden layer sizes, so the structure of the deep neural network, and you find in the slide deck, I have put this into an appendix, a bit of background, very basic introductory background with regard to deep neural networks. Simple shallow one usually has one hidden layer. Deep neural networks, 2 hidden layers and more. Easily 100 and many, many more. Here by default it is set to 100. So this would be the default, right? 100. We can go and, for example, add another hidden layer with yet another 100 hidden units. Right? So this increases what is called the capacity of the model, and usually we would expect that it's better able to capture whatever we want to have captured. You see now, instead of 500 milliseconds, now that I have increased the capacity, it runs much, much longer. It has also built in what you see here from the timing. User used 14.2, but the wall time is just 3.16. So you see, given the relationship here, that there's heavy parallelization going on. But this depends on the machine. So the M1s have 8 compute cores, standard compute cores, so it probably uses all of them in order to do the updating of the neural network. So if you have a 4-core machine, this might look different. You can also suppress the parallelization, but of course, usually we would like to have stuff faster rather than slower, right? And here, visually, I don't know, but we can have a look at the mean squared error, and this has at least decreased. It's for sure not perfect here, but I guess it's not much better, but significantly better, we can say. We see a difference here. We can go even further. As one more step, we can add more hidden layers or increase the number of hidden units. This might have some kind of natural limit with what we can achieve in this regard. You see the training time takes longer and longer, right? And now it's gotten worse. So good that we get to this point. Increasing the capacity of a model given a number of training iterations might not always yield a good result, right? Or a better result, I should say. Good is something absolute, but a better one to what we have seen before. And that's very often the case, that we cannot really judge things in absolute terms, right? We need to look at them quite often in relative terms, because for something like this, we wouldn't even know what a proper or good result is. There's nothing, you cannot pick up a textbook and say, well, if you apply this algorithm that way, that's kind of a good number. There's nothing like this is out there. It also depends on the use case. Some results might be perfectly fine for one use case, it might be well too bad for another use case. So all is relative, in other words, in such a context. We have natural limits. And I don't want to spend too much time on this approach, which in and of itself has a number of problems and issues. But what we can do, we can add the same thing. Here I mark this predicting stock prices ML. And I put this up front because this would be more or less like something that we often would apply. First, predicting stock prices based on OLS regression. Right? We can do this in the same way. We have now the features as the independent variables, the labels data set as the dependent variable. I always say variable. Somebody pointed this out. This is German pronunciation for an English word. Variables, right? We can do a regression out of the box like this. NP lin alg LST SQ ordinary least squares. We feed in, as before, the cols, right, the columns, and the symbol here, plus technical condition, -1. What we get here is a tuple with results. I'm more or less only interested in the regression parameters, not in the rest here, like eigenvalues. So these are the regression results. You see just the last one has significant weight. So the last one, I mean the most previous, like number 1, the last historical data point, or the most recent. Need to be careful how I name these things, right? When I now more or less in the same vein, after we have the model fitted here, embodied by the regression parameters, we can do the prediction. This would be done based on the dot product, data calls, and the regression parameters, so that we now get some values here, right? But we know this already from the numbers that we see here, that in order to generate the prediction, it will primarily take lag number 1, and the rest has close to zero weight, right? But nevertheless, we can do the exercise and store, or do it like this here. Data pret, I changed the name here, OLS, and store this in pret OLS, and then we can plot symbol and pret OLS. But I go now here already with ilog 100. Right. And this looks more or less the same, but now compared to our MLP regressor with 3 hidden layers with 100 units each, where at least my brain is not enough, has much more neurons than the neural net, but still I cannot understand what's going on. Here we have at least a path which is transparent enough for us to conclude and see what's happening. It takes today's price and uses mostly exactly that price to predict the future. Right? Nothing else is happening. Therefore, it is moving this. If you like, visually speaking, you have your time series and it moves it by 1 day in terms of the prediction. What it observes today is used as the predictor for tomorrow. And when you read the theory about efficient markets, that is one way of interpretation, right? In an ordinarily square sense, here in this context, the best predictor for tomorrow's price is today's price. In other words, no point in analyzing historical data. Right? We can also do here. Let me change this to pret MLP. Pret MLP. So should work, right? And I want to do the same here. The plot, yes. This is also pret MLP, and I want to do that one here with the ordinarily squares regression as well. So we have here a benchmark OLS. It's even lower, it's better. So that's not to say this is the way you should do it. This is rather now a basic framework which we can fill with life and go step by step and exchange elements of what we are doing here. So in the context of the clustering, ChatGPT taught us that normalization is important because clustering algorithms such as k-means are scale sensitive. The same holds true for neural networks. Not that much for ordinarily squares regression, but if we go here, and where are we doing this? Right? Let me put it in here and normalize the data as we have been doing before. Data minus data mean, parentheses, data standard deviation. We can now do the fitting with normalized data. I go here with the symbol itself, right? For the prediction, I need the normalized data, and well, it's now taking a little while. The result improves, but it's not spectacular, right? We could also go in the other direction, and this is by no means something that is a corner case, right? For some or many cases, we can even say in finance, smaller architectures, a lower capacity of neural network can be better. I don't know how it is here in this context, right? I don't know, but this can be, and I would never exclude saying, well, let's try bigger, higher capacity, or smaller, lower capacity. I would always go in both directions, depending on the problem, depending on the overall parameterization and the data set itself. One can be, improve results, or the other. But again, this is not like the major use case that we would like to have. In general, when we speak about a stock price prediction, what we in finance are not really interested in is like the exact same price. Although we are so used to this, right? The analyst, Mr. Müller from the German Commerzbank, sees a price target for Apple of XYZ, right? So they come out with these targets with prices, right? But as a trader, usually what you're interested in is the direction of how the price is supposed to move. That's good enough, because this will decide whether you go long or short. Maybe you want to know whether a big move is to be expected or a small move, because most of the moves, and we have seen this with the histograms in financial markets, are pretty close to zero. They're centered around zero. We have the high peaks. And that's basically for every trader, that's shit, basically. Even if you are right with the small bets, you won't be able to make your transaction costs back. Therefore, you need to get the large moves correct. And this is why the larger ones, the size of the move is relevant, but not really in terms of like 3 digits after the point. It's more like, right, big move, small move, which direction. This would be good enough. But I will only focus on the direction that's good enough, and not as we have done it here on the price side, but rather, which is theoretically and practically much better on the here it's with prices, right? Now I do the same with returns, which we should do with both ordinary least squares regression as well as the machine learning based approaches as well. So let's use this as a framework, and here now we go with the log returns. Before we can do that, I need the log returns, right? So I maybe start from scratch here with R, saying NP log. You've seen the definition today already with the discretization and everything, right? Log data symbol over data symbol shifted by 1. So this, in mathematical formula speak, this will be something like the natural logarithm of st over st minus 1. This is what we do here. This is the programmatic representation. All right. Let me maybe also start here with a redefinition, PD, so that we don't have the old stuff in our data frame. Start from scratch with data raw symbol. After the symbol, the log return, and speaking of direction, I define after the log return the direction. That's now an easy thing since we have the returns. I go with sign of data R. All right, this gives me a +1. So data hat. This gives me a +1 when the return is positive, and it gives me a -1 here when the return is negative. Right, just simple, but nevertheless helpful and useful function in NumPy. Sometimes, for my eye, I like to transform this into integers because it gives us here, you see, given the non-value, it gives us floating point numbers. So, but that's now our basis, and D will be our labels. This is what we now try to predict. From our estimation problem, we now turn to a classification problem. Before it was about prices. But again, even for the traders here, where we see prices on the screen and basically only prices, we have color-wise the direction. Right? Not really here with the Heikinashi, right? That's a mixture, but when I go with the standard candles, now green and red are the direction. Right? Red, red, red means down, down, down. Red, green, red means down, up, down. Right? And this is what we want to predict. We don't want to predict what the closing price is now, but we want to predict whether the next candle is green or red. So instead of +1, -1, we could have green or red. But of course, the machine works much better with numbers than with color names or whatever. Right? Maybe Matplotlib is, but different story. So numbers, colors, whatever is better for you to imagine, is what we now want to predict. But the major difference is from floating point numbers, let's say a gazillion options that we have on the real line alone between 0 and 1. We have an infinite number of options. Here, just 2. I think this is a little bit more simple, right? Up or down instead of like 50 centimeters, -30, whatever. So, now the lags can reuse the code here, and instead of the symbol, I take the returns. So I replace the one column by the other one, so that we afterwards have the price itself, the log return, the direction, and the lags. And now here we see it nicely. This is the label, and these are the 5 corresponding features. So we have a look at the historical returns. And here, not only whether they're going up or down, we provide the detailed information, but even with the detailed information embodied by the features, we want to just predict whether market goes up or down. If you would use, for example, TensorFlow, you would need to translate the -1s into zeros, and later on maybe getting back to the financial context, a -1, but scikit-learn works pretty well with negative values here as they are stored in the columns. So, drop NA, all stays the same. Here, data calls, data symbol, now needs to be replaced with R. Right, we want to predict. Now we can discuss, right? In and of itself, ordinarily scarce regression is obviously a regression, is an estimation method. I can feed it also categorical data. Maybe I simply do it for the sake of illustration. Right? We get the regression parameters, but what we cannot expect, and this visualization now doesn't make any sense anymore, right? And instead of the mean squared error, we need something else, namely here from sklearn metrics import accuracy score. What we're interested in is now how often does the model get the direction correct? Like when you go to the casino, yeah, I've placed bets 100 times on red and black, then somebody will ask how much did you win and how often did you win, right? What was your P&L and how many games did you play, right? And then it's like, were you correct like 3 times, 30 times, 70 times out of the 100. This is what we are interested in. So in and of itself, when I do this here, the prediction OLS, having a look at, let's say, the tail end of the data, no matter what I feed into the OLS model, it will always give me an estimation, although I have provided only plus ones and minus ones. Right? So no guarantee, not even, I mean, guarantee is far off from anything, even close to a guarantee. We get here simply numbers. But this now looks like we only get positive values. What I can show, for example, is the following. Since we are, no, this is not, I think, not helpful here in this, let me simply visualize it. I mean, whether helpful or not, we can decide afterwards. So pred OLS plot. We see, of course, we are not getting here just like positive values. The impression might have been natural here, right? We are getting other values as well, which are positive.
Predicted returns.
Sorry?
This is the predicted returns, the last column.
Oh, here I didn't replace that one. No, that's good. That's correct. No, I was wrong track. Back. Let's go through it. We are not somehow we are, but somehow not, right? Have a look here. We train on, what do we train? Now our calls are returns data, right? Before this was price data. Before we only had price. Features, labels, all was price. Now we have as the features, the returns data, and I train it on the binary label, on the direction, right? And I was saying, no matter what I feed it, it won't come up with directional output. It will come up with, because it's an estimation method, with floating point values, right? Therefore here, prediction OLS, let me see that there is no issue, data calls rec.
So if it's positive, you say, so how do you make a decision, like what's a good?
Yeah, therefore I was on the track where I was saying with the analogy to the casino, right? I've placed 100 bets, and then the natural question would be, how often did you win?
Yeah.
How often did you lose is then the complement. Right? So here I could also go, no, I leave it as it is. I don't want to compare it either to the direction nor to the returns, because this was not our goal, right? And now to your question, what we would do is the following. We would say data of the prediction OLS, right? And we would translate this now into directional data, as we did before, right? Take the sign of the prediction. Before we had the log returns, took the sign of the log returns. What we get here now is, right, like the values +1, -1. But now let me check. I've shown the tail. I just wanted to, maybe we go with the head so that I can compare this. For the head, we have plus, plus, minus, plus, minus, right? Plus, plus, minus, plus, minus. That's now the translation. We are now interested in how good this is compared to the original data set. Right? So this would be something like P to capture this, and maybe I show this here, P like 10, for example. So this gives pluses and minuses. And with the imported accuracy score, I can now compare data direction. That's the real data. And data, P, I've abbreviated simply by P. That's enough. And I get an accuracy score of 52.3%.
So this is all so far in sample, right?
All is in sample, yeah. All is in sample.
So may I ask you another question? It may be like
Sure.
on the tangent here. So if you go in, let's say, out of sample, would be the place here to kind of get into this reinforcement in terms of how much is a good gain in order to make this a true signal? You know what I'm saying?
No, not really. What was reinforcement learning in this context?
You know, it's like, let's say I want to train the model
Yeah.
in order to maximize some kind of return or risk-adjusted return in the out of sample. Would I use this like to tell the model like pick, for example, 1, because some value is greater than what I want it to be, but do not pick the next signal because it's noise. No?
Is a signal noise?
Okay.
Signal can be generated based on noise, right?
Yeah.
Um,
Okay. I'm just thinking to train the model from different point of an objective function.
Yeah, first, when you just think in terms of long-short strategy and risk adjustment, the standard deviation of volatility will be the same for your long-short as it is for the plain vanilla long, given that we have the square in it, so it's all squared. So whether you're above or below, this is like the other thing is, one of the most important parts here, what I was mentioning before, but now I can put it in context. 52% can be amazing or can be really bad. Because when we have here, right, the frequency distribution here for Netflix. When you have 50% predictions correct and they are all more or less around 0, this is not worth our while, right? Again, what we would like to get correct are here, the -20.
Yeah, this is what I'm trying to say. Like,
In the right direction.
can I train the model to forget
Right.
the middle?
Filter out everything that's insignificant.
Yeah, you could, for example, go with 3 classes and say, well, I give a +1 only for a return which is above a certain threshold. I give a -1 only which is below a certain threshold. I've done these exercises hundreds of times, but they never got anything better out of it than the plain vanilla approach. Therefore, I skipped that and almost forgot about it. But of course, you could do that. You could try to train it on the large movements only, right? When people ask me, how do you train models on extreme outliers, I said it's not possible, right? Because you don't have data to train it on.
Can you test your accuracy number against 50% for statistical significance? Like, because, you see what I'm saying?
Yeah, again, this is just one side of the coin. The benchmark would be a random toss of a coin, right? 50-50. This would be the benchmark.
Right.
From a statistical point of view. Here, I don't know whether this is good or not because the economic side is missing. This is where backtesting comes into play. We can answer the question easily, right? We can do data
Trading on this signal.
strategy return, data prediction OLS times data the market return. This gives us a strategy return. So meaning we get the market return when we are long and we get minus the market return when we are short. So and then I can do my standard. I basically don't want to really focus on this, but it's easy enough to do here.
We're just trying to retire you. I mean, I shouldn't speak for Evie, but speaking for myself.
No investment advice. You recall the disclaimer, right?
We're not asking about that.
So come some, apply the exponential function to get the log returns back into our world, right, and do a plot so that we see the performance over time.
So my question that I was trying to ask you was, can I use this last line of code as an objective function in the reinforcement learning to maximize?
Which last line of
This,
code?
like, this computation of the return, right? So this is the cumulative return of the strategy, correct? The back test.
Yeah, but this looks really weird.
I'm just saying, even if it looks weird, can I say this is going
Yeah, but what do you want to train with the reinforce? What do you want the agent to learn?
to learn, like how to pick, when to assign +1 and -1, based on the back test, so it can maximize this function.
Yeah, this is how it is done, but this wouldn't be related here to our ordinary least squares or whatnot. So you would train the agent and say, well, you get a reward in, like, let's say, 100 times your daily return, so that it's significant enough, and then it would try to, like an agent playing a game, tries to achieve a high score, right? It would try to achieve the highest number in terms of the sum of the log returns or whatever then the final measure is. But this doesn't need to have this as a preparation, so to say, or as a pre-processing step or whatnot, right? So, but still, I don't know why this is. Why is that looking so weird? The predictions. Of course, I need. It's looking weird for a reason. I need here the. I can use the P, I could use the P. Let's do the P here. Right? That's the shortest one. So that's now the cross return over time, and you see, yeah, it's more or less the same. So here 52% is not enough. But when you read the book about Jim Simons and Renaissance and Medaillon, right, you will read there that they, over time, over decades, they've had a hit ratio with regard to their trades of tiny bit above 50%, some 50.255. Right? Therefore, here, obviously, we are better than 50%, but not with the really interesting trades.
But this is
Right.
in sample, so it's really like how
Yeah, it would probably be worse out of sample.
will read that,
Yeah. But you don't know. Maybe out of luck, it would be good. Depending on what the out of sample is, but maybe let's, now that we have this here, have a look at the
This is why it's really naive, right? Because right now you assume that even the low probability 0.01 should be a buy compared to 0.55, where it's a stronger signal that you potentially should go positive, you should go long. Right?
Yeah,
So you could have cut off.
what is the probability here in the ordinary least squares model?
So no, right now you're trying to predict negative 1, 1. You're not trying to predict 0, 1. So it's not a probability. So what I'm saying is that a predicted y of 0.01, when you do it based on the sign, you assume that you should buy. But a predicted y value is a probability right now. A predicted y value of
Yeah, but this,
0.65.
you can't really interpret this as a probability. There's nothing in the ordinary least squares model which would give you.
Yeah, that's.
Now you're saying, well, again, that's like the discussion from before. Of course, you could say, well, we set everything that's below or above a threshold to 0 and skip that, going neutral, for example, right? But there is nothing like a. This is for illustration purposes. I wouldn't do it. In the machine learning models, you can look up, we can do that. You can look up the probabilities, what the model thinks about the prediction it is making, right? So it takes a little bit. We get it here, data normalized, model fit data cults, data direction, but I need now the MLP classifier. And here I need the classifier as well. Classifier. Classification, doing the fitting. Prediction data underscore calls. And again, this is now not of interest to us anymore. This is prices, or was prices before. Also that one not. But what we have here, maybe we can implement the very same thing. So that we have immediately the comparison. So it was here. This changed somehow. There's some things with Jupyter Lab. I mean, I love it, but some things are annoying. When I do this paste, it scrolls all the time now. This has never been the case before. It was fixed on the screen and then it pasted, and now it's like jumping around. Anyways, personal problems here. So the go up here, MLP. So we can go with MLP now. And this now gives us a block. Why is it giving us a block? Yeah, because this model now predicts indeed +1 and -1. Right, this is a classification model. Instead of like feeding it categorical values and getting back floating point numbers here, we train it on binary labels and we get back binary prediction. So that's not really, the chart here is not. We rather do a value counts, semicolon. And here we see only two values are predicted. Upwards movement 14 to 2 versus downwards movement 9 to 1. I don't need here the translation into signs, whatnot. Accuracy score, this already is the prediction, right? So data D and prediction MLP can be compared directly, and here we get out of the box in sample, of course, all is in sample, we get 67.8%. Much better, not a big surprise. This model is kind of like specialized on this type of problem. Ordinary discrete regression is misused, abused in the other context. You can do that, and with a little bit of tweaking, more lags, etc., you might get better results, but it's not for this particular purpose. Here, strategy return from the predictions, and you see how this is going through the roof here, right? Obviously not only gets like the tiny little movements correct, it gets also the larger ones correct. Maybe I simply decrease here the capacity of the model in order to make the results worse. 67 to 55. And this is still even impressive, but we might be inclined to believe in that picture a bit more. Although we shouldn't believe in anything that we see here. I'm not giving a disclaimer about what Evie was pointing out a couple of times, because this is just in sample. Right? But this approach now, where we are and this is from a conceptual point of view and theoretical and mathematical point of view, very important one instead of prices. What people would do here in the charts, we are dealing, as we should, with stationary values, meaning the returns, the log returns. And instead of trying to scientifically somehow predict the values, the levels themselves, we are focusing only on the direction. The one is, from an algorithmic point of view, the right way to go, and the other one is an absolute simplification compared to what we tried before. Of course, we have the situation, and we can address this now, we can have a look at this, that we probably want to trade, or we might think about only trading when the model is, let's say, pretty sure enough. We have this here in the form of predict probability, log prop we could look as well. And I think this is exactly what you mentioned before.
But, so going back to what I said before, I mean, if we think of the linear, for let's say it's a linear probability model going back to green, right? You could do the exact same thing there. Just
Yeah, you can.
0, 1, something like
Yeah, that's what I was saying. You can interpret it that way, and then you. But again, I wouldn't use it that way. OLS is not for. It's not for.
Oh,
that
yeah,
thing.
but conceptually.
Yeah. But here we see from the neural network we get real probabilities that we can look up. Here are 6 shown. We see many of them are clear-cut, some more, some less. We don't have any. Let's maybe show 10 in the beginning. Where we have here, for example, that's a case where the model is not really so sure, right? It says, yeah, 50.5 versus 49.4, but many of the other observations that we get here are like 42 and 57. We would expect that the model is pretty sure, right? 44, 55, same, 40, 59, etc. So these are the probabilities for one versus the other. Of course, this is then, that's basically the sequence of things, right? Internally, there are the probabilities. And from the probabilities here, we get a 1, 1, 1. We can compare now. It picks the higher, that's the argmax, right? NP argmax of the values that we see here. Finally. It's now showing here the way it's doing it, right? We have the probabilities and it takes the index value 0 or 1. Here in our case it is -1, so what is 0 here would be translated into -1, and that's the way it goes basically about it, right? We could now change a number of things. We have a ton of options with regard to our deep neural network, the MLP classifier in this context. We could have more lags for the ordinarily scarce regression, fewer lags. That's basically the only parameter that we have, right, with that method. Here we would have a few more. But I think in terms of an illustration of supervised learning, and we come to a more, how shall I say, reasonable example than this pretty simplified one. Let me just restart and rerun this whole thing, and then I will push it to the gist. I don't know, how is the mood and how are the spirits? Shall we do a little exercise and apply what we have just seen? Somebody, okay. So what I was thinking is a little competition or game, right? So not amongst each other, but against the efficient market hypothesis. And this only makes sense what we are now going to do when we, what he was mentioning now a few times, do a proper train test split, right? We have seen already that in sample, right, only in sample without any splitting, here the MLP classifier, for example, can easily be adjusted to be a perfect model, right? You can increase the capacity, do X, Y, that, and you will get closer and closer to 100% correct, right? This is the typical case of overfitting. The proof lies rather in, proving that out of sample, in a generalization sense, a model can perform well. Good, let's say, better than something, right? Therefore, the first thing as a benchmark would be to generate. You can pick maybe another symbol instead of the one that I would. What did I pick? Did I pick Netflix? Google, yeah, you see it. We could have done the same analysis with any symbol. It doesn't really matter. You can pick another one. You can work with Google as well, or maybe Apple is your favorite, or you want to work with a bank. You add to the whole story a random walk, and you implement the analysis from A to Z with the A, the random walk, and B with the, if you choose the MLP, there are many other options that we have, but here you have the code already more or less given. And yeah, see what you can do in particular here. So this is where the focus should lie on. No? InSample is more for informational reasons, right? Maybe you can skip that. So I can put this in brackets because InSample you can always, it's not a link markdown, thank you. Even if you do a train test split, you can also calculate the numbers on the training data set, which is InSample for the training data set, right? But the major point here is the test part, right? And how this looks given your random walk versus your market data, right? Happy Python coding.
You push this, right?
I push it, yeah. Git. Let me check. Change a few things. Git. So it should be available on GitHub. So if you pull, you should get the latest version. I often do the exact same thing when I discuss efficient markets, and I show that in the least square sense, the best predictor for tomorrow's price is today's price, something that we have rediscovered today. And all the results that you get from real-world financial time series are exactly the same that you get from random walks. Right? So this is what the random walk hypothesis is about. But here we are now. I mean, in the 60s, we haven't had MLP classifiers, MLP regressors, right? But in the 60s, there was ordinary squares regression. Basically, this is around since Gauss 1780 something. Used least squares for the first time. Therefore, we shouldn't give up too early to believe too strongly in efficient market hypothesis. I mean, I've given a talk last year about that.
So going back to my question, so here I can actually, in this InSample, rather than, I can try to train it, so rather than trading every day, I can say trade to find the optimal number of the window over which if I trade, I'm gonna maximize the return. So rather than, it could be every day, but it could be every 3 days, or it could be every 5 days, and it's probably it will be dependent on the stock that I'm trading. Can I find like an optimal trading window?
I can imagine, yeah. So what is in this context that you're describing? There are models out there that are multi-layered, right? You might have one model which takes care of the prediction. Mm-hmm. Let's say this is the deep neural network. Often reinforcement learning is then used as a trade execution engine, saying that's the signal. And now the point comes that I wanted to make. Often they train it on the optimal position size, on the sizing of the position, which is more or less what you say.
This is where reinforcement learning will come.
Reinforcement learning, this will take as input the prediction of the model, and then decides whether to trade, and if to trade, what is the optimal betting size.
Right.
This can be modeled as a control problem, like from 0 to 1, so fully invested or not invested or everything in between. Or you say I have just like 5 brackets of investment, like nothing, a little bit, a bit more, even a bit more, and 100%.
Because in this kind of a picking, then I can choose like, let's say I can pick the window based on the maximizing the return, but I can also pick the window based on minimizing the biggest loss that I can have. So some kind of to cut off my losses. You see, just to change the learning, maximize the profits or minimize, some biggest drawdown or something like that. This will go in the reinforcement, because reinforcement should have like an objective function, right? And I'm training the objective function.
Yeah, but you must take care of not formulating conflicting objectives, right? So
Yeah,
if the major objective is to maximize profit,
Right, I agree, then that's it,
then everything else
I agree.
you wouldn't really care about drawdown, right? So
Agree with
it hopefully is indirectly second order somehow involved. Again, with regard to your argument, what I would say again, like I said, position sizing, but also when you include in the whole story transaction costs, right? This then decides probably your optimal trading frequency. If transaction costs are 0, you say, well, I don't care, right? I trade 1,000 times in 10 years, so who cares? If you have high transaction costs, which eat up small profits, then you would say, well, no, I cannot trade that often, right? And this is what a reinforcement learning algorithm can learn quite well from feedback.
Like where the reinforcement learning comes into play, and I guess it's like after the prediction is done.
Yeah, this is what I was saying with multi-layer. So that you might have different algorithms that take care of different things.
Do you still have high transaction costs in Europe?
Do you what?
In Europe, do they still have high transaction costs? Because over here, I mean, at least for day traders, not high frequency, the transaction costs have been minimized as much as possible.
Yeah, but small transaction costs, we know this since Black Scholes, right? If you trade often enough, they can be as small. Yeah, therefore intraday, with regard to Wanda, for example, when you trade FX, etc., this all looks like large movements here on the screen, right? But they are tiny movements compared to the spreads that you see, at least as a retail trader, right? And even for large traders, that's not insignificant, I would say. Right? You need to have some movement in order to make. But of course, again, it depends on the horizon. If people are trading on daily technicals, for example, it's completely different stories than on 1 minute bars. So we have in the past implemented so many algorithms on different time scales, and with the retail pricing of Wanda and others, 1 minute, even 5 minute bars, it's hard to even earn your transaction costs when you trade so often intraday, because have a look at the distribution, and this is even more so intraday, right? The peaks are even higher, right, intraday. And you also have the fat tails, because like when you have something, then you have like 10 larger movements in a row in terms of the 1 minute bars in general. So that's not like market microstructure, and the impact on profit and loss is not trivial. Right? But this is where you can combine all the methods that we're covering here into a larger, more complex trading system.
So since it's 3 o'clock, do you think that we can also do the, what else? The supervised learning, or it's for tomorrow?
This is supervised learning.
Yeah,
Or what
yeah,
do you
like what-
do? You mean the advanced examples, or?
Yeah, well, the tomorrow will start at, I'm just kind of, since I'm not gonna be tomorrow, I'm kind of greedy.
Yeah, sure, I see. Yeah, therefore I was asking whether you're up for a little exercise, and I saw a few nodding,
So
and
for tomorrow will be the advanced financial examples.
this is all today. This is planned for today. So I can keep the financial data API stuff short. This is for tomorrow. That's all about generation, reinforcement learning, natural language processing.
Recording this one.
But again, it might take until I'm back home to, hopefully I don't lose my machine on the way. Usually I have everything on Dropbox, right? But
Yeah.
I said like this morning from yesterday's recording, I was finished around 3. p.m. and this morning when I opened my notebook, it says uploaded an hour ago. So it was uploading all night. But the
Yeah.
problem is with screen recording with QuickTime, this high resolution, not a compressed format. For like my 2 hours 45 minutes of CQF lecture yesterday was 9 gigs. If I would record this with GoToWebinar in a compressed format, which is lossless basically, for full HD, so it's not 4K or whatever here the resolution is, well, that's good enough, I guess. This might have been 500 megs or something. Right? So I used to have a converter, but I don't know. The last time I checked, it didn't work at all. So I might get another converter where I can compress the recording first and then upload it. I mean, compression tower takes a while, but not like 9 hours.
Especially on only ones.
Yeah, this should be fast, but last time I checked it, everything it was giving me back wasn't really compressed. So I was not amused and not impressed by the non-compression.
How do you feel about really stupid questions? Stupid Python question. So I've got a scalar installed, and it's telling me, so I can't even,
Does it install with sklearn? Because the name is scikit-learn.
okay. SCI. KIT.
Scikit-learn. That's the.
As SK? Learn?
No. That's fine. No. This is the installation.
Okay, that's the problem. You were probably exactly right.
Oh, it's not installing. Let it do its trick.
It didn't? You don't think it did?
It should be, yeah. No.
Successfully installed.
Yeah.
Okay, let's see if that worked. Look at that son of a bitch. Okay, thank you. It's just been sitting there.
Yeah,
beating my head
package
against the wall.
names. Package names are yeah. I've had a random walk which was somehow predictable. I don't know what was happening there. Wasn't random after all. Has anybody implemented that stuff or no? Maybe I have coded one possible solution to it. Here, surprisingly enough, that's a pretty good example here. I like that. With this data set, I haven't worked like this before, so I have a couple of data sets where I can really do some data snooping because I know it so well. I know which strategies will give me roughly which results, but that's new. But yeah, includes data since yesterday. Most of the time I'm still dealing with data which ends end of last year. But here, just by incident, so maybe a quick run through because we indeed don't have that much time. I haven't answered all the questions, but I have created here a random walk, right? I've added this to my raw data set. Of course, when I repeat this, it gives me another random time series, right? It's just one, and it changes all the time. I could fix the seed, but it's really about the randomness itself, right? Here, I pick out symbol apple now, so I could also go now with random walk and implement the same analysis. I have now with two different random walks before. The first was good on the test side, and the second one was bad. So also this is random, right? Outperform significantly, underperform significantly. So exactly how the random walk is. It's like when people go to the casino and they win at the roulette, they say, well, I got an edge, right? I had a breakthrough. The roulette
Really
is
good at roulette.
predictable, right? Yeah. So of course you can have that. And there are people that have a winning streak over. There's like the survivorship bias, etc. It's always like, I recently thought this, and I'm also one easily tap into that trap. When they ask billionaires what their secret is, it's absolute survivorship bias, right? They say X, Y, Z. How would they control for, right? All the other people who did the same shit. Like, you know, as a kid, I was thinking of Mars, like Elon Musk and here and there. There are only that many Elon Musk and only that many Warren Buffetts. Anyways, so here I take Apple, right? do the lagging with R as before, do a split here at 80%, meaning 80% for training, 20% for testing. Very simple thing. The only, from a conceptual point of view, what we need to take care of is when we do the normalization of the training data, which is based on the statistics of the training data, the mean values and the standard deviation values, that's plural, right? For every column in the data frame, they become part of the model. That's an integral part of the model itself. Therefore, I need to normalize my test data set with the very same mean values and standard deviation values. So therefore, I first pick them, then apply them, take test, and then do the normalization. Here, the MLP classifier, the only parameter set to 1,000, train underscore, called so normalized data, but the real directional values, accuracy score on the train data set, that's the in-sample part that I mentioned. I don't need that to do on the whole data set. I can just check on the train data set. We see numbers from before, like for 65%, whatnot. Not realistic out of sample. Do the prediction, test calls, value counts, more upwards movements than downwards movements. On the test data set, right, we see here just 48%. So well below, we can say 50%, not even 50%, but, and that's the reason why I like this particular example here, and it's not fully reproducible due to the random initialization of the deep neural network. So, but this is a good example now where I say, well, it's well below 50%, but nevertheless the outperformance is significant on the test data set. So this is like the two sides of the coin where I mentioned you can get all the tiny movements correct. It doesn't bring you any further. If you get a bunch of the big movements, this is what in hedge fund speak is event driven, right? I'm expecting earnings announcement which will surprise markets, and this will get a big move in the stock price, whether up or down, but a big move. And if I'm on the right side, well, then I make a killing. It's not even tail risk. This is just like the size of the movement. Tail risk, a la Black Swan and Nassim Taleb, is more like protecting with options, really against the tail or whatever might happen, right? But here you see 48%, but nevertheless a fantastic outperformance. Not bad, right? But again, when I repeat the exercise, let me try it here. I only need to start here. So model instantiation without a fixed random seed. We have different weights. It has a different starting point. You see the number here is, instead of 64, is now 65. This changes already. Here the prediction, not that much, but it changes. Accuracy score out of sample, not that good. And here you see also not as convincing as before. Still not too bad, but a completely different P&L curve than we have seen before, right? So ton of randomness just for illustration, and yeah, let's do it with a random walk maybe. So this was part of the exercise. Now our object of choice is not tradable whatsoever, but the programming side applies. And here the numbers are similar, right? Same accuracy in sample, random walk, because it doesn't matter for the machine, right? It doesn't know where the data is coming from, randomly generated or not, right? Here, test even better, 50%, right? But that's now pretty worse. We saw like 48% going through the roof, and here, but here we need to be careful. The accuracy ratio for the random walk might have tremendously different implications, but because we now have the normal distribution. We don't have the high peaks, we don't have the fat tails. Therefore here it is a different story compared to the financial markets. But it's always nice to contrast these things. It behaves like the same thing. If nobody would tell you what data we are dealing with, oh yeah, that's okay, it looks like a financial time series, right? This one is a little bit, I don't know, weird. I wouldn't, yeah. This could be some mean reverting quantity, I don't know, a gold ETF or whatnot. Maybe one last walk through, random walk down Wall Street. I wouldn't expect the numbers, yeah, to be changed that much here. 50.7, yeah, slight outperformance, but not spectacular here, in particular with regard to the cross performance, right? So here you can play around a little bit, of course. Everything is simplified here. That's no transaction costs and whatever you can now start putting into practice. So let me commit this. Exercise sample solution added.
Thank you.
I'm not going to push it. I keep it on my machine.
Okay, now thank you.
You're more than welcome. All right. We don't need a break, no, right? Simply thinking of Evie, who's not there tomorrow. We might move on. So simple financial examples, a little bit of an exercise here as a marker, efficient markets, random walk, financial time series. Now some advanced financial examples. Again, the option pricing example is under the header of revisited from my last year's visit with the normalization. And credit scoring is something new. I retrieved the data set from Kaggle, which was anonymized, so obviously no names for credit scoring. The data set is relatively large. It comes compressed, but it has, 304 features and one labels column with the credit scores. And I don't know how many hundreds of thousands of data points. So I took this and created smaller ones, but still they are nevertheless large enough, I think, to have a meaningful example. Not like my 14 names for the clustering, right? It's a bit more. So let's have a look. Advanced examples. Machine learning for finances here. Where is this coming from? This might have been from last year. I missed that one. See, this is the appropriate header, right? I don't know why I didn't change that here. Advanced. So do some imports, suppress warnings. I don't know if there are warnings. Sometimes I leave stuff like this in there. I hate warnings, so when I see other people's notebooks with tons of warnings, I didn't like when people hand in final projects and I see 10 warnings. I can like, oh my goodness. But that's a personal thing. So warnings have their meaning, they're important, right? But I hate them. So estimation. This is now an estimation example, like we started with our historical price points and tried to predict the future price point based on historical one. So it's an estimation procedure, and this is about how to use a deep neural network to price options. It's what we would call model free, right? So the Black-Scholes model is a model, right? We start with some major assumptions. Let's assume the stock price follows a geometric Brownian motion with a given start price, which is a boundary condition with a couple of parameters. And from there we take it and do either analytical stuff, heat equation, etc., what you recall maybe from the ChatGPT discussion, or we do some Monte Carlo simulation or whatever. Here I use more or less the model side as a starting point and then train deep neural network to learn how to price an option. We have features, these are the parameters from the Black-Scholes-Merton model, and we have labels, these are the prices from that model, right? But without knowing anything about stochastic differential equation, partial differential equation, dynamic hedging whatsoever, hopefully the model will learn how to price it. So I create, with the help of the little script here, which contains a function called BSM. I use call value, and as simple as that. We have an initial value, 100. The strike price for the call option is 105, so out of the money. Horizon 1 year, so T is in year fractions. R is the short rate. We are almost back, right, with overnight rate to 5%. For years, I needed to teach stuff like, let's set it to 0, maybe minus something, right? When I implemented the pricing library DX Analytics, it really checked for positive interest rates and was raising a value error when somebody tried to put in a negative rate. But yeah, times have changed in between. But now we are back to like what you will read in the papers. And like long story short, the 2001 paper assumes 6% for R throughout, basically.
These guys don't remember that.
No,
They think
that's
this
like,
is an anomaly,
yeah.
that our interest rates are really high.
I had a friend of mine, I still have it, but he had an apartment that he bought, I don't know, 15 years, 18 years back, 20 years maybe, I don't know. And he told me the story all the time. He was so lucky back in the days. He got a mortgage of 9.99%, just below 10%. There were times, right?
Yeah.
I remember the late 80s, man.
Yeah. We are on the way there, right? Here in the U.S., what are mortgage rates now? 6.5 something? 7 already?
30 years, 7.
Oh, here we go. Here we go. Everything repeats itself. So, and sigma, the volatility, so 5 parameters. These are features, right? Feature, and the label we see here is 8. So now I generate via LinSpace minimum value, maximum value, and a total of 4 data points. 80, 120, and 2 evenly spaced in between. For K, the same. For simplicity, I take N throughout like the same thing. For the volatility between 10% and 30%, right? So what do we have here? N, what is it? 5 to the power of N or N to the power of 5 combinations? What do we have here? Here in that case, everything is N, but I show here you all, not all, some of the combinations. What is done now, we take the product of, for example, this is for illustration here, you see down here, I take the product of all the 5, obviously, 5 times 5 times 5 times 5 times 5, right? So N to the power of N is it, isn't it? But for illustration purposes, you see here just the combinations of S and K. Right, 80, 80, 80, 93, then 93, 80, 93, 93, etc. So we go over all the combinations. Of course, when I increase N to 6, we get many, many more possible combinations. And this is now the core label generating process, right? I go over all possible combinations, calculate the value, and store the feature values plus the labels values in a data frame. That's pretty quick, right? So we have here now 1,024 entries, right? Features plus value. Like we had it before, but now it's not some lags or whatnot. These are real values. In a reinforcement learning context, these would also be the parameters that would describe the environment, right? The training environment, for example. And the algorithm was supposed to learn, I don't know, in the dynamic hedging context, what I'm going to do tomorrow, how to hedge such an option, right? So that's the head with all the combinations, and I do my normalization. That's the important part. That's important here. So, what do? We have features, we have labels, supervised learning, right? I use MLP regressor. That's not the only method that we can use here, right? We could apply others as well. And the metrics here is mean squared error. So I calculated it before manually, I said, so I wrote the code for the mean squared, but we have this in sklearn metrics already as a pre-packaged version, right? I go with 512, so 3 hidden layers with 512 hidden units. The init is the init learning rate is 0.001, which is the default, by the way, and ReLU is also the default. The features here, F, what I was saying, these are the 5 parameter values, and I fit now the value on the features data. Right? This takes a little bit. You can imagine we have 1,000 data points. We have a relatively large, at least for such a small machine, a relatively large capacity for the model. 17 seconds wall time, 1 minute user time. Again, parallelization is our friend here. And the estimate is now gained from the prediction where we feed the parameter values, right? So, a cursory look. Yeah, and I think we can agree that the values are not exactly the same, but they are, numerically speaking, about the same, right? So when I get the mean squared error here, it's 0.004. There's not that much. And depending on the parameterization, we would observe like larger deviations or smaller deviations, right? With option pricing, and this has nothing to do with MLP here or what we use, what method, whatever. This is often the case even when you calibrate the model and then try or use the model to recover market prices. Some are better approximated or estimated than others. That's simply something we see often. Here, this chart, here, what shall I say? It more or less only says that we get the green line over the blue line, so we don't see that much, right? I can try here to go as I did before and zoom in quite a bit. So I log minus 50, for example. It looks pretty good here. So just when I get closer, you see here is the blue ones, right? So there are differences, but they are not that large. Maybe to illustrate this a little bit better, let me maybe do something like this. This should illustrate this better. How is this called? Data. I take these two. Data value. Do it the other way around, data, because I want to really work estimate. So these are the differences as an histogram, right? So although the charts might imply something else, we see here in part relatively large, but most of the differences, and that's what we would like to have, are pretty close to zero, right? The mean, the mean squared error here, 0.004. So the model is indeed capable, and the results that I presented last time around when I was here, they weren't that good. Here we see a couple of blue ones, right? But overall, we could say that's a good approximation. The model is able to learn, just given the parameter inputs, to generate like option prices without having ever heard, seen, or whatnot of the Black-Scholes-Merton model, with, of course, numerical derivations. Now let's use TensorFlow Keras. I think that's the first time that we use it, right? Importing TensorFlow. Let me just show, because this is often something of importance. Import TensorFlow as TF. TF version. So I'm working here with 2.11. The code might not work with the most recent ones. The code might not work with older ones. So they are changing it every time. So every release, 8, 9, 10, 11, 12, they change the API.
By the way, is there an easy way to have it load in graphics card for TensorFlow?
Yeah, yeah. To some extent, using Keras, it will try to access the hardware that is there, the preferred hardware, GPUs, but you can set the device as well.
Okay.
Yeah. So the model here is dense neural networks, deep neural network, deep in the sense of 2 layers, right? 64 hidden units. It's not like my, how many were there? 3 hidden layers, 512. The capacity is much, much lower for that model. Here, of course, this is, I wouldn't say arbitrarily chosen, but it should somehow show that we don't need that much here. So doing the fitting step with the TensorFlow model also takes a while, 11 seconds, quite a bit faster. The estimate here is generated by model predict data underscore, so we work for sure here with the normalized data, right? Here we can also check, yeah, this 5 cents difference, that's pretty large. Here it's much lower, right? The mean squared error here is much larger, right? Before we had 0.00, am I right? Yeah, I think there were three 0 digits. No, it's just 2, it's lower. I was remembering that we had 3 zeros here. So it's half the error that we have seen before. And when we plot it, we don't see that much more, so let me maybe copy that stuff from here as well, so that we see this in more detail. This scrolling drives me nuts. So this used to behave completely differently. And here, now we would need to have a careful look, but alone from the distribution, you see that it's different than what we have had before. So overall, we can say with that approach, we learn with the deep neural network, given the input parameters, the classical ones without the dividends, so this would be rather an index than a stock paying dividends, or maybe, I don't know, the FX rate or whatever. Without paying dividends, we are able to pretty well approximate here the values. I can also here with TensorFlow, this is always a warm start. If I don't re-instantiate the model and I re-execute here the fit step, it will start at the state where it left off, and it will do here now another 1,000, right? I can do that, the same thing with selected models in scikit-learn as well, but here it is the default. Maybe this improves it a little bit. Yeah, and now from 0.002, now I recall my numbers, it has decreased the mean squared error to 0.0005. So it's just a quarter of what we have seen before. Here we don't see a difference. Here neither, right? And this now is even more centered around. You see, it in particular has improved on the right-hand side, right, with the positive deviations. Left-hand side not. I could now go and do more, increase the capacity. I'm pretty sure we could get here to a pretty high accuracy, not the right word, to pretty low mean squared error in this context, right? But the major problem that we face here is in versus out of sample, what we have discussed before. When we train such a deep neural network in sample, we basically, given appropriate parametrization, can get to, in many cases, to 99 or even 100%. That's possible, right? Also given mathematical results like universal approximation theorems, which apply to certain kinds of deep neural networks. Generalization is another point and problem. So here, this is an in sample, and these two are out of sample. We now could come up with more, right? So this is, I think, the very first of all the ones, right? Just as a reference, I create here a data frame, call this option 1, option 2, option 3. Have it now in the format here. I do some do the normalization from before, right? Now I have my normalized values to do the training and do the prediction, and here we have the 3 predicted values. We have three sets of feature values, 3 times 5, 3 values to be predicted, and the first one here is 2.45, the original one, and here we have 244. So this should be something that's probably seen here as well. Yeah, that's the one here. You see 80, 80, 05, 1%, 10%. 2.45, 2.44. So that's I could have chosen any other example here as well. And given the results, the improved results that we have seen, we would expect these prices to be, the estimate being pretty close to the value itself. Not a market price, it's a value based on a model. Right? But now what about the other ones? These are now options which are not from the data set, right? And I've kept it like constant with regard to S and K as well as T, but I change here the interest rate and I change the volatility values. So here you see 7.51, not too bad, right? 3.99, here it is undershooting. So out of sample, it's pretty bad, so to say. What we could do here in order to improve this is getting maybe a wider range if this is an issue that we want to price something which is beyond, let's say, the volatility range that we have covered, or we make it more granular, right, so that the interpolation between the extreme values is better. So, but this depends then on the use case. Overall, I would say this is not too bad here what we see, right? We could come up with additional examples, etc., and test it, but the point is, without knowing anything about what options are, what the model is behind the pricing, such a deep neural network can learn quite a few tricks, if you like, and here the trick is pricing options. If not so good out of sample, that's okay, that's debatable, but roughly this is all in line in the right direction. And still we have a very small low capacity model, not that much training, so this is all, let's say, just a starting point. This was nice because the data set was created on the fly, so we could do this on our own. And like the sample data sets from scikit-learn, it's always an easy thing when we can do something like this. So now, I mentioned it already before, the credit scoring example is one that is about classification and where the data set is given by somebody else, which is a typical situation, right? Often you could ask immediately, what is the point of generating your own data and then learn something about the data? If you can generate it, you probably know what the law behind it is, the data generating kernel, right? So this data is from Kaggle. So when I click on this, you might know they have a ton of data sets, and so I'm not signed in, but here you see this is 14 MB, but this is zipped, right? So when you unzip it, it is, I don't know, has 50, 60, 70 or whatnot. Alone from this point of view, I have decided to just go with a subset. Okay, I got it. We provide you with a data set in CSV format. That's good. We know how to deal with it. The data set contains 8,000 train instances to 2,000 test instances. There are 304. I don't know where the 8 and 2,000. Is this the right one? because I think the data set is 65,000 or whatnot. It's probably rather 80,000, 20,000. So we can check immediately. So 304 input features labeled X001 to X304. The target variable is labeled Y. And this is like a typical competition there. Take a task, create a model to predict the target variable Y. A report, PowerPoint presentation, any custom code you use, instructions, blah, blah, blah. And you need to be logged in order to download it and to take part in these things there, right? I just wanted to make clear where I have this data from. So here, I hope proper attribution as compared to my disclaimer with regard to JetGPT. So the following data sets are smaller subsets of the original ones. I doubt that it's really 8 and 2. It's a little bit larger, but we can check immediately. So this is hosted on the server. Kaggle credit score train. That's the first, but that's a subset of the first one, and the other one is a subset of the second one that they give you access to. So the train info, and this is how I remember it, right? 62815. And as I recall, before I trimmed it, it was like 80,000 or even more. So the numbers that you read there are well too low. And what I also did, because there is no real point in having 300 instead of 30 for illustration purposes, I just took like 10 features out of the 304. And when we take a look at them, we see a nice mixture, right? The first one is a large integer. This looks like, I don't know, like a customer account number or whatnot, right? For a bank, I don't know. Internal number, a unique identifier, let's say, of the data set. Then we have whatever they stand for. So there's obviously no information with regard to what it is, right? What X002 is in the end. 426, 163, 112. I would need to come up with some, I don't know. I don't have an idea, but that's not the point here. And then we have categorical data. So that's a mixture here, right? We have large integers. We have here the floating point numbers, features, and we have categorical features, zeros, ones, twos.
Sorry to interrupt. To speed up kind of the processing through the machine learning, would there be any benefit to setting some of the categorical data as like int 8? If you took like the descriptive stats of them and they don't go past 2 digits, versus int 64 if the data set was large enough. Like, would keeping the memory overhead lower of the data set itself improve the speed of the calculations?
Probably not that much. Maybe on a large scale. So typically what you're describing is a standard approach when you work on GPUs, for example, when you say 30-bit is perfectly fine.
Yeah.
For what we want to achieve, and this speeds up for highly parallelized processes, right? And particularly also for the data transfer between CPU and GPU, this speeds things up. But here now going on the data frame side, this is all pretty small here, and change this from int 8 to whatever. To some extent, it might even do this internally when it reads it in and checks the data.
Yeah.
But let's see, do we have no? It has just, no. Here I see the counter proof of what I was saying. It's simply going with 64 throughout by default. We could now do S-type in 32 or 16 or even 8 when we just have low numbers. But I wouldn't expect that much of a speed up. You see, this whole data set here is 5.8 megabytes.
I guess it
Tiny data.
matters when it's in gigabytes.
Yeah, on a larger, From a memory point of view, in any case, computational speed, I would need to check. Interesting aspect. Maybe you can do that. So, it's easy enough to change the D-type here and then to look at it. So let's train head. So the what I'm doing here, this was driven. I tried to apply XGBoost here as one method, which often produces pretty good results, but it was complaining that the labels weren't contagious. That's the reason why I was checking here, right? This is the labels histogram, right? So that's like starting at 300, and you see, I don't know if this has a particular meaning, right? So credit scores, I would guess that the larger the better, maybe the larger the worse, I don't know. In Germany, usually in Germany we wouldn't deal with that. But in any case, no matter what here, larger, better or whatnot, the machine doesn't care, it just wants to get the results as good as possible in terms of the accuracy. And what I'm doing here, I just move the first 5 forward, then I'm replacing here values, and I go, this is a dictionary, right? I create a dictionary, do some replacement here over the data set. Because it's like, I don't know why it is, maybe due to the selection that I've done, it was like 300, 301, 02, 04, then 05 was missing. Obviously, there were only 05s in the other data set, the other data rows that I somehow dropped. Therefore, I move 300, 1, 2, 3, 4, 2, 3, 1 until 5. And then I subtract 301, so that we have in the end, after this adjustment, again, I don't care what 3, 4 means instead of 3, 5. I just wanted to have the numbers here in rows, so that we now have the value starting at 0, going up to 300. This was going up to something like 500, right? Do the normalization on the training data set, and here I haven't even included the test data set. We could do that as well, or you can do this as a little tiny exercise. Importing accuracy score, and this says MAP classifier. Oh, I wasn't working with the classifier. It was somehow too slow and too bad somehow. Decision trees. It's not a technical term. Let me do it like this. Yeah. In the end, I use decision trees, which are wonderful in so many instances because they are fast to train and pretty good in many instances. So let's maybe here use just a standard decision tree classifier before we get to the ensemble method. So here the decision tree classifier is down here instantiated. The only parameter that I set is maximum depth, 35. Maybe let's start with something smaller, 20. Model instantiation, model fitting, prediction. So these are the 3 steps. 2 seconds doing the prediction, and the accuracy score, it's pretty low. It's kind of bad, right? 34%. But let's see whether this all is on the right path. You see it predicts quite a number of 237s. Here it's the largest, the highest frequency. And when I do the plotting with an alpha value, you see the frequency distribution of the predicted values, and the original ones are only in certain parts. You would say this is somehow close to reality, to the original data set. But as you might have guessed, changing the maximum depth, let's go maybe in a few steps, 25, because it's so fast to train, among others, one of the major benefits, just by increasing the depth from 20 to 25, increases the accuracy from 32, doubles the accuracy, right, from 32 to 64. When we now have a look, now it looks like the shape is somehow correct. It doesn't get all the bins here of the frequency distribution correct. It seems to be a little bit heavy on the left-hand side and a little bit weak here on the right-hand side. So going to 30. Accuracy 86. Yet again, significant improvement. And now I think we would agree that's looking kind of close, right? To what we have here. And again, we shouldn't forget that the original problem was about 304 features. Now we are dealing with 10 features only. Feel free to work maybe with more, see what happens, right? And 35 was the last one. I don't know what the final accuracy was before I did the changes there. So now we are at 95.8%, right? This is now pretty much, fitting it kind of well. And still, this model is trained in 147 milliseconds. Pretty fast for 65,000 data points. And pretty good, right? We can do the same with TensorFlow Keras. We have 11. Do we have 11 features? Why it is 11 features? Length of train columns -1. I don't know. I thought we would have only. Did I say we have 10 features? Maybe I was like. This is like. I don't know why it says 11 here. Let's see if this runs through. The model looks similar to what we've had before, but there's a major difference, right, to the other example with TensorFlow. Here I go with a number of labels, which means the output of this model is 540 values.
You're
Yeah?
including the prediction from the prior model.
Could we
You
get?
didn't reinitiate your train dataset, so you have the prediction in, no? Because we create a new column here, the prediction, it goes in your next one. That's why you.
Oh yeah, that's true. That's true. That's the P1, right?
Yeah,
That's the
yeah.
11th. I did it in here. I use this as a. Must be, but this somehow worked before. Let me check. 10. Train.
You did a good job. Since
Columns.
passing the predictions from private.
Yeah, this is like foresight in financial market.
But the other prediction column from the prior model will be passing as a feature here.
So let me see. What is it? Complaining about sequential is incomplete expected non-10 phone shape non-11. This can often be the case when I was working on the second example, got back to the first one and didn't check the code afterwards, right? Because there was the header, right, MLP, and later on I changed it to decision tree and the other stuff. Creating variables on a non-first call to a function decorated with, I don't even understand what this is all about. When I re-instantiated the model now, it seems at least to run. Whether this is all now correct, it's debatable, or we need to wait for it. But it seems to work. Thanks for pointing this out. I was immediately surprised, right? 11? Doesn't make any sense. This now is a little bit tricky, I would say. I'd rather go. It's still running and running, right? Now we are used to 2 seconds, 1.6 seconds, something, right? And the model is not that large, 128, but 540 values.
How did you decide on changing from 64 to 128 here? I mean, do you have any?
Yeah, usually I play around, as I was saying, going larger, going smaller. That's what is called hyperparameter optimization, which is not really deciding. If you have been working on a problem since years, right, you have your feeling for the correct parameters, but that's like the discipline that you would use, right? You would work with different number of layers, different number of hidden units, per layer or different numbers for every single layer, or you would even change the optimizer here, Atom, right? Maybe different activation functions, which might work better. So these are all what is subsumed under hyperparameters. Right? It's still fitting here. What is the Epox 250? So as good as deep neural networks are, you see here with this problem, a decision tree model, much more simple and much faster, might do the same trick, right? Sometimes you try to work with the cannons and the birds that you don't need to win the battle. So maybe we don't need to wait this out. But as far as I recall, it gives a pretty good result with that parameterization. So I've now added here the re-instantiation of the object so that we lose the P column, right? Or not lose it, simply start from scratch there. Yeah, while this is still learning, and this is already on a relatively fast, at least desktop machine, and you see it's taking a while, depending on the machine that you're using, might take a bit longer, or you have, I don't know, I think you have somebody has a gaming machine with an NVIDIA engine, NVIDIA card in it. This might be much faster, for example, right? If it takes the GPU as the device to which to train it on. So with TensorFlow, not a big deal. I'm not aware of any kind of functionality for scikit-learn to train models on GPUs, but maybe they will introduce it at some point. I let it run. So given, here we go, 3 minutes. It feels like ages, right? It's just 3 minutes. What I need to do here is I need to predict now on the train data set here as I was training it. It must be -2, right, to be in line. I changed this afterwards. But for this run now, and the accuracy, no, there's something went wrong here. So that is, I reinstantiated here. So let me go with reading the train data so that we start from scratch. This is -1 for 10 features. Now we, I think, are in line. Then we have the length of the Y column. Right here, we do the normalization of the training data. Here I can get back to 1. This was the other place. Now I do just a few iterations, maybe 10, just to see whether this works, runs through. No, that one, -1. Better document the graph execution. What is complaining now? Receive the value. Oh, on the training data set, I need to do. That was the reason why I changed it here, right? This little exercise needs to be done here as well before we do the rest. R planes train. I think these two are enough. Let me try. I had TensorFlow like XGBoost. I had the case first with XGBoost, but TensorFlow was complaining about the same thing, right? Yeah, now it's getting.
The version that I downloaded was AdaBoost, AdaBoost.
Ah, yeah, I didn't go into that. The decision tree classifier you saw was already pretty good. I was playing around with the ensemble method, meaning that we can have, let's say, 5, 10, 15 single decision tree classifiers combined into one, then have majority voting or whatever algorithm. This is in many also financial examples. This can give you a real boost to the ratios, to the matrices that are relevant. So I didn't show it here because simply by changing the parameter here, you easily overfit here, so I'm not testing out of sample, right? But it shows that the classifiers are A, pretty flexible in these contexts, and B, pretty fast to train, right? Not needing to wait for like hours on end, it's just like a few seconds. And here now 8 seconds just to check that, whether it runs through. Again, here need to get back to the original code. Yeah, when we now have a look at the values here, it's by far not on a level which is like meaningful, right? You see it's still all jumping around. Now we would need to, I let it run in the background now with the iterations from before. When I go, you need to leave already, Evie? You have to, oh, I'm not going. Maybe 5-minute look at the data set. Where is it? Here we go. 250. This was the original one, right? Now I rerun this whole thing. But I open the next one, the final one for today, data API. So the data that we have been working with, not the Kaggle one, the ones before, EOD prices, EOD fundamentals. Right, this is now the Jupyter Notebook with which I have created that data. Here it's EOD historical data. That's the web page. Here I'm in my account. You see I have, alone this morning, I have done 1,315 calls to the API of my 5,000 limit. I have no financial interest with these guys apart from having here a marketing account, which means I get the 5,000 daily API calls for free from them, because I've used it a bunch of times last year here in many talks. And usually I'm not in the business of promoting APIs, services, whatnot. Even in our program, we generally have only fixed data sets that are generated and that are used for reproducibility, for not running into issues, so like why finance. My experience over the years with these APIs haven't been that good, and in particular, if you want to have something good, it's usually pretty expensive. So speaking of Refinitiv Workspace or Bloomberg terminals, all wonderful, but prohibitively expensive for most, apart from the fact maybe if Bloomberg here is sponsoring 20 terminals and I don't know, API access. But speaking of costs, they provide really comprehensive data, financial data, starting with typical end of day prices, but also fundamentals here, 60 plus exchanges, live data, splits dividends. What else do we have? There's much more down here, real-time API WebSockets, also for cryptocurrencies, extended APIs here for intraday data, exchanges data, so with, let's say, fundamental data for the different exchanges. Fundamental data also is pretty detailed, so the highlights is just one table that I have out of a gazillion of different data points. There are additional packages, right, and the all-in package, all-in-one package, that's basically everything that they got, is €80 per month. In the US, it's 80 US. So I don't know if it's 20 pounds in the UK. But here you see, for me, it's like I'm locked in as a German guy. 80, and you can save like 20%. So it's just like 10 months. €800. And what they offer is amazing, down to option pricing, etc. Right? Here we have calendar, data feed, bonds, etc. So in the all-in package, that's really attractive. So again, I'm not a salesperson. I'm not getting anything apart from the free account, quote unquote.
Daily day?
Oh, they have everything. Intraday, live, everything.
Options?
Yeah.
Oh.
They used to have, there is the, where is it? Search. It doesn't show options anymore. Maybe they skipped the options part. I'm not sure. Maybe they have now a separate or
Asking for more money?
add-on option. Yeah, options data always used to be.
Always expensive.
if I would have gotten $1 for every email that was asking where can I get free options data. Yeah, could be that there have been some changes with regard to the options data. I'm not sure, but everything else, like intraday, in particular crypto, they have like everything. And when we have a look, this is now still running. The other thing here, right? Where are we? Not the 12 seconds. This is just a quick check. Yes, still fitting. So what I'm doing here, I use my own EOD key. You can create easily an account and you get your trial account with a certain relatively low number of API calls, but basically you can use the budget to get started with if you're interested in. Right here, let me restart that. What I have added to the repo is what we currently call TPQ EOD. As much as I like the API, the service, etc., also the pricing I find attractive. At least from my personal point of view, as more or less disappointed and to some extent annoyed I was with the Python wrappers that have been available. So a colleague of mine, Michael, has written now a wrapper, which is our own. We are not fully finished, but I would say 90% is there. So here I run the creds, I import our TPQ EOD. That's part of the repository. I create here an API object based on the key. And these are now the data sets that I have shown you before, right? Pandas, they are the tickers. Simply a list that I have manually typed there, and I iterate over the tickers and retrieve the historical data starting from 1st of July. We have seen the data set, right? 1st of July going to the last available day, and this is now the data. We have inspected it before. There is now no surprise. I just wanted to show you this is now retrieved from the API. The other thing was a saved CSV file that I created out of that. Right, so I can also do the visualization, and you see amazingly, right, here NVIDIA, how this evolved over the last couple of when they got above the 1 trillion benchmark there. That's how I saved it, and then pushed it to the server. Stocks, the same thing. Here was complaining about a empty table that was delivered back, but it's not relevant for the highlights that we are interested in here, right? That's now for 5 symbols, the data. Or I have also, this is also on the server and commented out, I think, in the Jupyter Notebook, where we did that. For example, when you want to get fundamentals for a complete set of constituents, right here the table components, right, you can see here that's the German DAX index. It used to be DAX 30, these days we have 40, so they included 10 more recently into it. Here's RWE, DB1, DHL, Deutsche Post, right, Deutsche Börse, right, financial services, financial data. What we're interested in here is what they call code. That's a symbol or the ticker. And that's the way I retrieved the fundamentals now for a complete set of constituents of an index, right, 40 ticks there. This, of course, takes a bit. I think that's the longest operation here. And this is then increasing the number of my API calls here, right? When I do this over and over again, it hasn't been updated, right? Now you see here my API calls from 1300 to 1800. So when I repeat this notebook 5 more times, I've eaten up my API calls here, right?
And then it cuts you out.
And what?
It will cut you off.
Yeah, then you have the option to pay for something. I mean, I could call them and say, listen, I do like so many demonstrations, like give me more. But so far I've never run into any issues in this regard. Right? So now just a quick run through so that you can see all of this as well. Available exchanges. they have it on the page, 60 exchanges, and here are a few of them. Yeah, not a few, these are the 60 ones, right? Like BE is our Berlin one, and a few, most of them I don't know, but we can always look up here the fundamental data about the exchanges. Like here, this is the Zagreb Stock Exchange in Croatia, that's the Berlin Exchange in Germany, or we can get by putting all, like, everything of interest, right? So we can also look up the tickers that are available for the single exchanges and could use this also to retrieve data, fundamentals, whatnot. We can search for a symbol that we say, yeah, give me everything that has something to do with Tesla. Be it a bond, be it a stock, be it, I don't know, ETF, you name it, right? And here we see common stock, ETF, etc., right? So getting, and it's limited to 25 now, so there must be obviously some more, right? Economic calendar splits here, right? I don't know what the code is standing for here, what in particular. Here for earnings, IPO splits. I think this is double here, IPOs, right? Historic splits and dividends. For Apple, we have seen a couple of splits in the past. That's the reason why we always want to work with, or usually want to work with, adjusted closing prices, so that we have the splits reflected. You see here there have been 4. Also the historical dividends. This is now 80 rows, roughly 40 years, right? So that's for that. Historical tick data. This doesn't go that far back. I think this should work here with the 2nd of, here we can go here with, let's say, 6, which would be yesterday. Let me do it with the day, with the yesterday's data. This is only available here for US exchanges. So that's, I would say, kind of typical that the granularity and the breadth and depth of the data in the US is usually a bit higher than for other ones. Then also technical indicators. Here you see we've got now tick data for the 26th 6th of October, right? Here it starts at a certain point in time, it ends at a certain point in time, right? This is intraday, and we have retrieved now quite a bit, 813,000, right, for Apple for a single day. I would need to go a little bit deeper if this aftermarket or whatnot, how this really works, what they include here, also with regard to market prices here, the shares, the volume, I would say, at this tick. So since this, I got this version from my colleague yesterday, so we are still, but again, I hope it's 90%. Sometimes you think it's 90 and it's just 60, but he should have a good overview of the API now. Technical indicators, I don't know why they've added this, because technical indicators, at least for me, is something I get the price data and then I have TALib or whatever I want to use or code it by myself. But they provide here indicators out of the box, like simple moving averages. I don't know why, but the API gives it back. And it's a relatively long list: split adjusted average, volatility average, blah, 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 blah. You see quite a few things. I don't know if this can be really customized, right? Where do we have the call here? Yeah, here, this is what I meant by customization. Period 7 means obviously simple moving average over 7 bars, right? Also live data. Here it starts a live stream. You see this is asynchronous, right? It sleeps. The sleeping here is when you execute the notebook completely, right, from A to Z. The sleep is meant to stop it, collect the data in the background so that you have some data. Otherwise, you wouldn't see here when I do it manually, this problem doesn't arise. But you see we get here, we get the large number of data points for USD, for example, or BTC. This is now the second stream. Again, it sleeps 5 seconds, same reasoning, while the sleep is added in here. We have now in our object BTC USD plus from before ETH USD, right? Ton of data in the printout. So I can, of course, also access just one of the two, and what I get back is a data frame with which I can do visualizations or whatever, and this closes the crypto stream. That's not everything that the API can do and that we have implemented so far, but that gives you like an overview. And yeah, with regard to the fundamentals data, there's so much. We have quite a bit of work has been gone into writing a data class, particularly for the fundamentals data, because they provide a ton, like in a format which is nested and nested and nested again, right? So that it's hard to retrieve that and put it in a data frame or put it in whatever, right? You need to parse then the single tables that are in the JSON format, like, you know, this nested JSON format. But overall, again, for researchers in finance, I think this is really a good value proposition, what you get for that pricing compared to Dow Jones, Refinitiv, LSEG, and Bloomberg, and some more out there. For research purposes, that's good enough, I would say. I think so, for many research projects. For the big hedge funds out there, I mean, they have anyways budgets in the millions for data. And in London, I have discussed quite a few times with the guy responsible at Goldman for data procurement, right? They have a complete department which doesn't anything else than to procure data for all the people. That's a different story, but I think here we are happy to get good quality data easily for an attractive price. And we have used the data out of the box in a fixed form, but you see, if you want to get anything else, you say, well, I'm interested in that name or in this here, left and right. That's easy enough. Maybe I'll leave it here so that we have it executed on the in the repo. Something is wrong here. Something I need to revisit that that thing here. Something is, either I do the prediction wrong or I need to check. So maybe I do this tonight after having had some dinner. And yeah, it looks, maybe I just need to rerun it. Now you see it's much closer than before. So another run of 250. I think this is what I did before, like 500 might give us the result. But in any case, we can conclude this is much, much slower than the decision tree classifier that we had before. Anyways, I leave it for the time being as it is. Push it as it is. Let me check. I've changed these two. Yeah. Changes, advanced examples, and
I'm not gonna thank you yet.
API.
I learned. I could be trained. Does anybody want some of, there's like two muffins left. I cut them in half to serve out.
In any case, hope to see you tomorrow, right? Before we know.
I gather
leave.
that I will email you, you know,
Sure.
because you're here next week, right? When you find out, Thursday? Wednesday?
Thursday.
Okay.
2nd November. Thursday, right?
Yeah, I think it's Thursday, yeah.
Thursday.
I'll
Yeah.
email. So I got my friends are kind of.
Yeah, maybe we can have some food in the evening, some more simple one. I think last time we
I'll
did.
text you. I'm back Sunday night, so
Okay,
I'll text you when I
okay.
get back.
Great, great.
But